Hello friends, good morning one and all. Okay, to the last lecture we have covered unit number 3. Today we will going on the unit number 4. Okay, then in the unit number 4 you have given the first part is a torsion and second part is given buckling of column. First we will complete the second part, which is buckling of column. Okay, you know what is meant by column. In this unit we will cover this theory part. First is a column, then strut, then crushing load, then crippling or buckling load. It is also called as a critical load. Then after that, types of the column. There are two types of the column: long column and short column. Then there is some theories are given. First theory is a Elur's theory for. This is given for only the long column. Okay, this theory is not applicable for the short column. Then some assumptions are made by the Elur's theory. We will see the details which assumptions are made by the Elur's theory. And after that, effective length. What is meant by effective length? What is meant by slenderness ratio? Then how to calculate the crippling stress, and what is the limitation are given for the Elur's formula. One by one we will cover all these things. Okay, first is a what is meant by column. Column we will draw. Okay, column is nothing but vertical structural member. Column is a vertical structural member carrying a compressive load. Okay, column is nothing but the vertical structural member carrying a compressive load. This is called as a column. Okay, this is the main part of the structure. Column is a main part of the structure. It is a usually long as compared to the cross section of the column. Cross section of the column, and it fails due to the buckle. It's failed due to the buckle. Okay, all of you getting the what is meant by column? Yes, column is a vertical structural member carrying a compressive load. Only the compressive load. It is known as a column. And what is meant by strut? Strut is a member which strut is a member carrying an axial compressive load. Strut is a member carrying an axial compressive load. Okay, it may be short, it may be vertical, it may be horizontal, it may be inclined. Okay, strut is, it may be horizontal, vertical or inclined. Okay, it is the one type of the rod. Okay, when you apply the some load, then there is a compressive stresses are induced. It is a usually short in length as compared to the column. Check, the length of that strut is very short. Also, there is a no possibility to buckle that strut. Okay, there is a no possibility to buckle the strut. If you are applying some load on that column, because this is a long, this will be buckled from its original position. But strut is a suddenly fail. They are not buckled. Remember that. Okay, it may be horizontal, vertical or even inclined. This is the difference between the strut and column. All of you getting? Then next is a crushing load. Crushing load, the load at which member fails by load. Okay, or by crushing only. Okay, the load at which member fails. The load at which member fails due to the crushing only. This load is called as a crushing load. Crushing load. So this is the original length of the column is given L, and when you apply the some load, the end of the column is P, then this will be filled due to the crushing load. Okay, this load is called as a crushing load. What is the crippling or buckling load or critical load? The member which buckle from its original position due to the applied load. This is called as a buckling load or crippling load or critical load. This column is buckle just from its original position. This type of load is called as a crippling or buckling load or critical load. Okay, all of you getting the difference between the crippling or buckling load? Yes. See, if you are applying the some load, suppose this is the column. Okay, we will apply the some load. Okay, then what happen? This column will buckle from its original position. This type of load is called as a buckling load. This type of load is called as a buckling load or crippling load. Then after that, types of column. Types of column. There is a long column and short column. What is the long column? Long column is nothing but the ratio of effective length. The ratio of effective length to the least effective length to the least lateral dimension is greater than or equal to 12. Is greater than or equal to 12 is known as a long column. Okay, how to identify the given column is long column or not? You have to check the effective length. It is denoted by the effective length. It is denoted by the LE, and least lateral dimension is LLD is greater than or equal to 12. Okay, this type of column is called as a long column. This value is greater than or equal to 12. Okay, then we can say the given column is a long column. Okay, then this it is filled due to the buckling only. Okay, this long column is filled to the buckling only, not crippling load. Okay, what about the short column? This the ratio of effective length to the least lateral dimension is less than 12. Is less than 12. This type of column is called as a short column. Since this LE divided by LLD value is less than 12, then this type of column is called as a short column. Okay, all of you getting the difference between the long column and short column? Yes, clear? This short column is filled due to the buckling as well as a crippling load. Then see what is the Elur's theory for the long column. We will see the Elur's theory for the long column. This Elur's theory for the long column is Elur's theory for the long column is filled due to the buckling only. Okay. This theory, Elur's theory, is not used for the short column. Okay. Then what about the crippling load? You will get in that theory, Elur's theory for the long column, you will get the crippling load is denoted by PC. PC is equal to pi square EI divided by LE square. Okay, pi square EI divided by LE square. Then you know the value of the pi. What is the E? E is the nth modulus or modulus of elasticity. What is the I? I is nothing but the least moment of inertia. What is the least moment of inertia? You know the radius of gyration. In the form of radius of gyration, I is equal to AK square. I is equal to AK square. I is equal to AK square. Remember this formula. PC is equal to, very important formula, what is the Euler's theory for the long column? You will get the crippling load PC is equal to pi square EI divided by LE square. What is the I? I is the least moment of inertia is equal to AK square. Okay. LE then all of you getting the Euler's theory for the long column. Here you have to remember that Euler's theory of the long column is failed due to the buckling only, and this theory is not applicable for the short column. Okay, then you can find out the crippling load PC is equal to pi square EI divided by LE square. There is derivation is given. I have skipped this derivation. No need of the derivation. You have to remember this formula. PC is equal to pi square EI divided by LE square. Then next is the effective length. Okay. Before going on effective length, there is some assumptions made by the Euler's theory. When we use Euler's theory, then what is the assumptions made by the Euler's? Okay. First, the column is remember that column should be axially loaded. Okay, this column should be axially loaded. This column should be axially loaded. First is the assumption is that axially loaded. Column should be axially loaded. Remember that. Okay, column should be axially loaded. Then what about the material of the column? The column, if you have checked the property, column material is perfectly, already we have seen that assumptions, homogeneous, then isotropic. Material should be homogeneous, and isotropic. Also, one more material required for that assumption, elastic. Second assumptions, you have to remember that material should be elastic, homogeneous and isotropic. Okay, thus obeys the Hooke's law. What is the Hooke's law? The stress is directly proportional to the strain. This law will be obeyed in the second assumption. Then the third is the column should be perfectly straight. Okay, column should be perfectly straight. There is no bend in this column. Perfectly straight and uniform in the cross section throughout of the length. Okay, this cross section is uniform throughout the length. This is the third assumptions. Okay, self weight of the column is neglected. We are not consider the self weight of the column. Self weight of the column is neglected. We are not considering the self weight of the column. Self weight of the column. Column should be long. Okay, next assumption is that column should be long. Column should be long. Okay. The column length will okay, what we can say, the column length of the column is very large. If you have compared this length of the column is very large as compared to the cross section of the column. As compared to the cross section of the column, length should be long or greater than the cross section of the column. You have to remember these assumptions made by the Euler's theory. Okay, all of you getting the assumptions? Okay, this column should be axially loading. Okay, what about the material? Material should be elastic, isotropic and homogeneous. Okay, this material obeys the Hooke's law. Okay, self weight we are not considered here. Then column should be long. Then column length should be very large as compared to the cross section of the column. Okay, these assumptions are made by the these assumptions are made by the Elur. Okay. Then next is what is the effective length? What is the effective length? Effective length is the distance between. Okay. This is the effective length. This effective length is denoted by the LE. Okay. This distance between the point of contraflexure in the column. Effective length is nothing but the distance between the point of contraflexure in the column. What is the point of contraflexure? We have seen the unit number 2. Okay. When you apply some load on this column, okay, then suppose I will give the one example. Here is a suppose both sides are hinged. Okay, and we are applying the some load, compressive load P, both end. Then this column will be bent from its original position in this way. Okay, suppose in this way. Suppose here is a sign changing in this position, then we can say this length is a effective length from its end. Okay, remember that. Here we get the sign changing of this buckling of the column. That's why this effective length is a LE. And so you have to remember that this is the distance between the point of contraflexure in the column. Okay, this is known as the effective length. Then next is a slenderness ratio. Slenderness ratio is denoted by the lambda. Okay, lambda is equal to, it is the ratio of effective length to the least radius of gyration. Radius of gyration is the denoted by the k. Okay, what is the LE? LE is the effective length. What is the k? K is the least radius of gyration. Radius of gyration. Least radius of gyration. And lambda is denoted, slenderness ratio is denoted by the lambda. Okay, you should remember this formula. We require this formula. Then we move on to the kind of the crippling stress. Okay, in the form of this crippling stress. Okay, how to calculate the crippling stress? You know the general definition. Crippling stress, or it is also called as a critical stress or buckling stress. How to calculate that? In terms of, we want to calculate effective length and radius of gyration. This radius of gyration. Okay, this sigma CR is equal to, we know the crippling stress is equal to, I can write it is the ratio of the crippling load divided by cross section area. Cross section area. Then how to calculate the crippling load? We have seen already in the Elur's theory for the long column. This crippling load is denoted by the PC is equal to pi square EI divided by LE square. Pi square divided by LE square. Okay, pi square EI divided by LE square. Then what is the I? I is equal to what? I is equal to what? We have seen in this equation. I is equal to what? I is equal to AK square. AK square. This is the least moment of inertia. If you have put in this equation, then you will get the sigma CR crippling stress is equal to pi square E divided by lambda square. Pi square E divided by lambda square. Again, what is the lambda square? Lambda square slenderness ratio is equal to LE divided by K is there. LE divided by K is there. If you have put here, you will get the AK square, right? AK square. This is the value of crippling load. I will write directly here. Take that pi square E AK square divided by LE square. Okay, I will rearrange this equation. Pi square E A divided by LE divided by K is there, bracket square. LE divided by K means again lambda square is there. Okay, and what is the cross section? If you have put the cross section area also denoted by the capital A, capital A. This A gets cancelled, you will get the pi square EI divided by LE by K square means lambda square. Getting? This equation gives the crippling stress in terms of you will get the effective length and least radius of gyration. The last point is a limitation of the Euler's formula. What is the limitation of the Euler's formula? We will see limitation of the Euler's formula. Okay, all of you getting? Yes. The next limitation of the Euler's formula. Check that this crippling stress is directly proportional to the elastic or we can say the Young's modulus. Okay, and this crippling stress is directly proportional to the modulus of elasticity or Young's modulus. Also, that crippling stress is inversely proportional to that what slenderness, square of the slenderness ratio. What is this formula? Sigma CR is equal to pi square E I. What will get here? Pi square E divided by lambda square is there. Okay, what is the limitation of the Euler's formula? Therefore, that I will explain. What will get the crippling stress is equal to pi square EI divided by lambda square. Okay, this crippling stress is directly proportional to the modulus of elasticity or Young's modulus, and it is also the inversely proportional to the square of the slenderness ratio is there. Okay, then this Euler's formula is applicable for what? Euler's formula is applicable check that if this crushing stress it is denoted by the sigma c is greater than or equal to this crippling stress. Remember that. Okay, then or we can say the buckling stress. If the crushing stress, or I will write here, if the crushing stress is greater than or equal to the buckling stress, then we can apply this formula. Euler's formula is applicable if crushing stress is greater than or equal to the buckling stress. Okay. Sigma, then how to calculate that value? Sigma c is greater than or equal to pi square E divided by L divided by K square. Lambda square means what? LE divided by K square is there. With the help of this formula, you can check this Euler's limitation of the Euler's formula. And how to solve this? Check that LE divided by K bracket square is greater than or equal to pi square E divided by sigma is there. And LE by K is equal to what? Root of greater than or equal to pi square E divided by sigma c. You have to check the slenderness ratio. LE by K means what? Slenderness ratio is greater than or equal to this value, then this formula is applicable for the given numerical. Otherwise, this formula is not applicable. Okay, if you are getting the Le by K value is less than this, then this formula is not applicable. Okay, you can take any example for the mild steel. Suppose sigma C value is given 330 MPa and suppose E is given 2.1 into 10 raised to 5 MPa. Okay, if you are putting these two value in that equation, okay, in the mild steel, okay, this stress is induced 330 MPa and modulus of elasticity is given 2.1 into 10 raised to 5 MPa. Then here you will get this value, sigma C and E value. If you have put, then you will get this value is a Le by K is greater than or equal to 80. 80 is there. 80 is there. Okay, when slenderness ratio is less than 80, suppose slenderness ratio is less than 80, then this Elur's formula is not applicable. Getting? Very simple. You have to remember all these basic things. Okay, then next lecture we'll see the ranking formula. Okay, also we'll see the different conditions. Means suppose you have given the one side is free and other side is fixed, or both sides are hinged, then what is the value of crippling stress? We want to find out that with the help of derivation. I will skip the derivation part. Directly we will go through that formulae and solve the numericals. Today we will stop. Thank you.